cybersecurity, and false data injection. Uh, this week, we're going to speak about the demands, which is an important aspect of smart grids. So what does generation side management mean? So the traditional power grids are top-down oriented and only try to manage the system by controlling resources at the generation side, meaning that we usually just have control on the power plant and the generation side. And if we want to control uh, the power in the grid, the only tool that we have is to control the generation to start, for example, a power plant. That's the easiest way to do it, or open a hydro plant. Uh, but we didn't have any control on the uh, load part. And you need to keep in mind that in electric power, uh, we have to have the same power in load and generation at all times. So we have to contain a constant power transition. So the electric power must be generated, transmitted, and consumed at the same time. Very important. If you generate more power than it's consumed, it's going to cause damage and problem. And it's the same thing if we consume more, that again, it's going to cause a lot of problem, damage our transformers, transmission lines, and so on. So traditionally, only the generating units are adjusted to keep the demand and supply balance instantaneously. Variable renewable brings new challenges as well because we don't have any control of that. So if we have a solar system, a solar power plant, or a wind power plant, we cannot control the generation side. So that creates uncertainty in the system as well. Sometimes we have cloudy skies, or the wind doesn't blow, or we don't have enough rainfall, even in if we have a hydropower plant. So those create problems. In a year or so, it's a short-term problem that we have. We may have like no winds in a week, no solar sunny days in a week or few days, or some years we don't have enough rain, therefore we don't have any water in the reservoir. So those create some uncertainty. So another approach is, instead of controlling the production part, we control the load or consumption part. So extra flexibility and more advanced control methods are desired. Therefore, demand side management, or what we call DSM, provides system operators an additional option to manage the grid. So instead of just having control over the production, we also have control over the consumption or setup or the load. So DSM program consists of a group of strategies that are designed to encourage consumers to modify their consumption level and pattern throughout a variety of methods, such as financial incentives. DSM can change and flatten the load profile. DSM encourages end consumers to shift their consumption from peak hours to off-peak hours. The objectives of DSMs are to reduce costs, enhance grid reliability, and facilitate the integration of renewable energy sources. And DSM helps defer the need for new sources of power and network upgrade. And this is a graph that shows the impact of DSM. So as you can see, the demand side management programs include the energy efficiency, the time of use, and we're going to speak about each part, demand response and spinning reserve, which I would explain each part. And you can see the energy efficiency, of how much each has impact, the timing and the impact that we have. For example, an energy efficiency reduces the overall graph. Time of use reduces the peak hours. The demand response also manages peak hours. And then we have the spinning reserves, which kick in when we have a high demand. So benefits of ESM programs, it alleviates the congestion, commit less generators, it reduces the cost, it improves grid reliability, and it defers investments. So energy efficiency, we have heard a lot about this, is basically to reduce the loss in a system, and it is a key to achieving a sustainable energy system. And the overall goal is to reduce loss, as mentioned, and to reduce overall power consumption. And some examples of waste energy in the system could be a outdated old AC system or a dirty filters in an AC system, which puts extra pressure on the fan and the cooling, and the AC would run uh, for more time, for extended periods of time. In addition to that, the older generation ACs usually they use the HVAC systems. They use a AC motor. The newer generations they use brushless DC, which are more efficient. So newer generations are much more efficient, efficient, and with the rise of heat pumps, and the efficiency has increased significantly compared to the older generations, which just use a heating element. There's also compressed air leakage, low efficiency equipment like low efficiency lighting, low efficiency appliances as well. Like older generation, again, refrigerators, they just use an AC condenser motor for the condenser. Now they use a brushless DC or DC, which has a much lower power consumption. And some appliances draw power, which are called ghost appliances, like your TV when it's on standby, or your computer, your PC, or the electronics that are connected to the power and are on standby mode. They also consume some power. And simultaneous heating and cooling. Some people like to cool one room and heat the other room, and that creates a lot of waste as well. So energy efficiency is the efficient energy use that we can use. One example, as mentioned, is through a use of energy efficient uh, light bulbs, insulated houses. When you insulate house, you can reduce the power. By the way, the HVAC can consume anything between 30% up to 70% of the power uh, is used just for heating and cooling, depending on where you live and which type of HVAC system that you use. So it's a huge portion is just going to the HVAC. So having an installation that it's efficient, and having the house that it's very well insulated is going to help significantly with the efficiency. Also, newer generation energy efficient bulbs like LED lights. You can see different lights. And by the way, light is mentioned in lumens. Lumen is the amount of light that you get from one candle. Sometimes they call it candela as well. And so 450 lumens means the light is almost equal to 450 lumens. The higher the number is, you get more light or brighter lights. So this is a comparison between the standard lights, LEDs, CFLs, and halogen lights. You can see that how efficient LEDs are. For the same 100 watts, the incandescent lights, which is the consumption is 100 watts, LED is 19 watts. So instead of paying $13 per year for electricity, you pay $2.50. So 1/5. And generates less heat. So if you're in the summer, this generates, it's like a small heater, and it lasts much longer. So this is an example, an energy efficient 5-watt LED bulb saves more than 80% energy than a 40-watt traditional bulb, but provides the same level. And lifespan, uh, this is usually 1, 2, or 3 years. This is up to 15 or 25 years. So it's a huge save in both upfront costs and electricity. The other thing that is very important in demand side management is called the time of use. Most of you are already familiar with the duck curve. We want to usually shift the time of use of the power use to the off-peak hours. So the duck curve actually looks something like this, and this is the y-axis is the energy usage, and usually in the morning, and the x-axis is the time. So usually around like 8 a.m. And by the way, this is different for different environmental. So if you're in a warm environment, it's a little bit different. And this is like 5 to 9 p.m. So during the morning when people wake up, you have a sudden peak and everyone wakes up. They want to turn on their coffee maker, their toaster, and then when everyone goes to work and school, it dips down, and then in early afternoon at night, early at night, it's going to peak again because everyone's back. They want to turn on their lights, their dishwashers, and so on. So you're going to see another peak, and this actually looks like that's the reason they call it the duck curve. It looks like a duck, and uh, we want to shift these two uh, to the low demand as much as possible. So because we have a baseline energy production, usually these are nuclear power plants, large power plants, and at these peak hours we kick in, and also solar power. It's exact opposite of the duck curve. Actually, solar power looks a little bit like this, the blue one. We have a maximum output uh, at noon, the middle of the day, and then at morning and in the early afternoon, we have reduced power output from solar power plants. Um, so we wanted this time to be shift, and one way to do that is through financial incentives. We can have variable rates, and actually Amarillo has this. I think I've already mentioned this. For off-peak hours, we can say, oh, if you do off-peak hours, it's 7 cents per kilowatt hour, and if you do it, your consumptions at peak hours, it's gonna be 14 cents, for example, double the price. And that would encourage the consumer to move and shift their high demands um, to the off-peak hours. So if you want to turn on, for example, your washer dryer, your dryer, especially the dryer is a big element. It consumes 4, 5, 6 kilowatt hours. Uh, it's better to move that in the off-peak, so like after 9 p.m. Again, this 9 p.m. until 8 a.m. is again off-peak hour. Or if you want to charge, if you have an EV and you want to charge it, it will be much cheaper, half price to charge it over the night. So this financial incentives helps to flatten this curve and shift the peak hours. Again, the goal is to flatten the load profile by shifting some peak loads. And we also have demand response is a change in the electricity consumption to balance supply and demand. The demand response can lower the electricity price in the wholesale market and improve system reliability. It provides consumers an extra electricity plan option. They would get paid when asked to reduce or shift their electricity usage. This is being actually implemented right now in California. So in California right now, they have a weird problem actually. There's too many supplies of solar power, especially in the off-peak hours, and the price of electricity sometimes goes negative, and they actually want to send that extra electricity during off-peak hours to the neighboring states, and that's creating a lot of problem. Just recently, California has stopped giving incentives for new solar powers systems and stopped all the incentives for those programs because they have excess production during the off-peak and the peak hours. Again, they have a problem um, with lower supply because of too much solar power production. So market demand response is the real-time pricing, price signals, and incentives. It relies on certain markets where prices are formed and products are traded. When the price of real market RTM is high and RTM pricing is forward to consumers, they may reduce their electricity usage in a timely manner. In some places, the RTM pricing only exists in wholesale energy markets. End use consumers have a fixed electricity plan. So usually when you have a digital uh, power meter, uh, you have the time of the day use or time of use or TOU system. The older analog power systems, because it costs a lot to upgrade them to be able to uh, calculate the power during different times, they use a bulk flat rate price, which is an average between a lower price for off-peak demand and higher price for the peak demand. So we have the physical demand response. It's the grid management and emergency signals. The DR contracts will make consumer reduce electricity's usage. It sends out signals for mandate demand reduction when the grid is in an insecure situation or some components are facing outage or reduced performance. And we have the direct load control as well, which sometimes the consumers give consent to the power company to control some of the demand, like an HVAC, newer systems. This has been actually tested in California. So the power company could actually have control over your HVAC system or your grid, or your smart plugs, and for example, stop charging your EV when there is a lower, high demand, and uh, they could reduce your demand physically, directly. So spinning reserves by loads, it's exactly how it sounds. Spinning reserves is actually, we have some generators that are running and they are on standby. And when we have a surge in demand, uh, they actually add those an unexpected outage and demands. So typically, spinning reserve only denotes to available generation of online units in a given time period. We usually have reserve uh, generators that are spinning, and we just put them into the grid when we have a peak in demand. But it's as it's mentioned, it's very uh, somehow um, waste of power. So it's better always. It's going to be more efficient to control the demand side than have extra generation. Loads can also act as virtual spinning reserve if they correlate their consumption with the grid state and system events. This can happen in an autonomous way or in a coordinated way. This is again uh, an impact of improved energy efficiency versus demand response. You can see this is energy efficiency, which reduces the overall consumption in peak and off-peak hours. And this is the original consumption. This is for a certain area. Again, it's different for different areas. And we have the uh, demand response with rebound, which is this line over here. And we have the demand response without rebound. And the final goal is actually to flatten this as much as possible. So incentive-based demand response, we have the direct load control, or what we call the DLC. The grid operators have full access to some customers' appliances. It's interruptible, uh, curatable, curtailable rates. Customers get special contracts with utilities. And then we have emergency demand response programs, uh, which are involuntary response to emergency signals. We have capacity market programs. Customers guaranteed to pitch in when the grid is needed. And we have demand bidding programs, or customers can bid for curtailing at attractive prices. The FERC's definition of demand response is the change in electric usage by demand side resources from their normal consumption patterns in response to changes in the price of electricity over time, or the incentive payments designed to induce lower electricity use at times of high wholesale market prices or when system reliability is jeopardized. The key of the demand response is intentional changes in consumption patterns of electricity. It doesn't work always as planned. I'll give you an example. This is customer enrollment in retail demand response programs by region. This is enrollment in retail demand response from 2016 and 2017. In some areas, was an increase in participation and response. Some areas were a decrease. So you can see in Alaska, it's an increase. People prefer lower prices, but they're okay with the inconvenience of it. And in some places, like Texas, there's a huge, you can see changes. But in other places, you can see there's actually people went back to having a fixed rate. The reason is that it's a trade-off between comfort and incentives. Some people prefer the comfort to pay regular electricity prices, to have sufficient power supply. They don't want to reduce, for example, in summer, they don't want to increase the inside temperature of the home, or not be able to use their washer dryers during the peak hour, or not be able to use their iron or coffee machine in the morning. So they're willing to pay more. And some people prefer the incentives and lower electricity price, but shift their demand to off-peak hours. So when you have incentives, you pay reduced electricity price, but you have limited power supply occasionally. But it's cheaper, less convenient. So the other thing we have is the thermostatically controlled loads, or what we call flexible thermostatically controlled loads, or TCLs. As mentioned, a big portion of power consumption goes to heating, cooling, ventilation of homes. So heating, ventilation, and air conditioning systems, heat pumps, electric water heaters, and refrigerators can be controlled in these systems. Again, because these account for a big portion, sometimes 70 to 80% of the power consumption of a household. So even if you can reduce that by 10, 20% and move that to off-peak hours, it's going to have a huge impact. If you turn off the refrigerators for a few minutes when you're not at home, or a few hours, it's not like your everything is going to melt in the refrigerator. Or if you turn off the cooling for a few hours or 30 minutes, the temperature will not increase immediately, but it's going to have a huge effect on the bill. One example that I personally used was I have these circulating pumps on my water heater, and it worked continuously. And I replaced that with added a $5 smart plug that you can control, and times you don't use a water heater when you're asleep at night, you can just simply turn that off. So water heater is the same, another example that you can shift your water heater instead of going turning on the water heater all the time. You can limit the times of the use, and it's not like the water temperature will drop immediately. It takes like half an hour to an hour, and then you can shift that consumption. So TCOs are flexible demand resources. They possess a brief period where their power utilization can be altered without any significant impact on customer comfort level. They can be aggregated to provide demand response. They account for a significant portion of electricity consumption, as mentioned, around 70 to 80%. And they have potential to support power grid, provide grid ancillary services. So HVAC, the TCOs, we have the bang control, or from on to off versus off to on. They can frequently switch on and off. It's a simple but effective to offer demand response services. And the heat transfer process is critical to related to the electricity consumption of the unit. One example, again, you can turn off the HVAC during a peak hour and takes like half an hour to an hour for the house um, to the temperature to rise to a uncomfortable or drop to an uncomfortable temperature, and you're able to manage that. This is just a graph for heat transfer process of an HVAC system. So equivalent thermal parameters or ATP model, a thermodynamic model. This model is appropriate to be used for residential and small commercial buildings. And these equations, by the way, you don't need to memorize any of these equations. Just it's here for you to know. AT is the ambient temperature, Q is the heat rate for HVAC unit, W is the heat exchange factor for house objectives, and HC is air heat capacity, and so on. The key point here is to be able to control that. So you have to give consent to the power company to be able to have direct control, and the system must have the capability. Usually they have a IoT, they are IoT-based HVAC system directly connected, and you give permission for them to be able to control that. So the demand response support time, a metric to quantify HVAC-enabled demand response. It's indicating how long an HVAC will be available for demand response at a given time, or be used to identify the set of HVACs that are qualified to provide DR without compromising consumers' comforts. The HVAC thermodynamic model can be simulated to determine the DRST, or the demand response support time, for each HVAC system. This is an illustration of the metric DSRTs. You can see that you can set it between upper and lower bound temperatures. It's going to turn on and turn off. This is the normal without the DR. It's going to keep it with the lower threshold, close to the thermostat temperature. It usually goes up. If it's in a, if you want to heat the house, it's usually heats it to a few degrees over the thermostat temperature, and it will reduce around the set temperature. Is going to kick on again. When you have a DR system, it's going to leave the system to drop the temperature a few degrees below the set temperature and then kick it on. So you can see that instead of turning on every, let's say, 20 minutes, it's going to turn on the system every hour. So it's going to push the system and shift the demand side. So this is an example of when you assume a hot summer, and you can have opposite for hot summer and cold winter. That basically the graph is the same. So imagine we have a hot summer. Instead of dropping the temperature down to the set temperature, we leave it to run for longer periods of time. The HVAC is at on status during time periods T1 and T2 and T3 and T4. This HVAC is at off state during T2 and T2 and T3 and T4 and T5. So it's self-explanatory. With a DR signal is received at TDR start, the HVAC can provide DR until it reaches the upper bound temperature at the TNDR. The DRST is the time period between the TDR start and TDR end. Again, you can see, and as I mentioned, it's the opposite for the when you have a heating system, it's electric heating system. I'm not speaking about gas heating. So this is with the DR again, and without the DR, the system just cools down the system to a lower temperature and leaves it to go up. And you can see that's much higher time for the HVAC system to be turned on, and then it goes back. So you have a higher uh, more distance between it. So the HVAC should be turned on for a longer period of time. So you can see between T1 and T2 and T3 and T4 it's turned on, and between T2 and T3 and T4 and T5 is turned on. But with the DSRT and demand response, you can see that it's turned on, it reduces the temperature, but doesn't reduce it all the way down, and turns off, and so on. So the DRST, or the theoretically maximum DRST, it provides insights about how long each HVAC can support when they receive DR signals at extreme low points when cooling, or extreme high points, as I mentioned, with heating. When HVAC receives the DR signal right before those extreme low points, such as T2 negative or T4 negative, the corresponding DSRT is the TM DSRT. Like DSRT, TM DSRT is also affected by several factors, including the ambient temperatures. So this is the theoretically maximum DSRT for 100 small HVAC systems, and you can see the highest, lowest, average, median, and standard deviation for each of them. This is again just for you to know. And this is the HVAC demand response quantification method. That this is just again, it uses the HVAC demand response as a contingency response reserve, and the TR denotes the pre-specified contingency response durations, and PH denotes the power capacity of HVAC, and shows how the algorithm of how the system works. Again, this is just for extra information. You don't need to memorize any of this one slide. And then we have network microgrid with HVAC DR. The microgrid day ahead scheduling. These shows the economic benefits of a renewable energy penetration level. Scenario 1, it's without the HVAC reserve, and scenario 2 is with HVAC as a reserve. And you can see that how much different it makes in the price. With the base case of 25%, it reduces the power from 1,016 to 870, so $250 almost save in the power. And you can see that it creates a huge difference in the power bill. And the second table shows the reliability benefits. The average forced load shed for scenario 1 without HVAC as reserved in microgrid day ahead scheduling with tie lines is outages from is out outage from 21 hours to 22 hours in real time. So again, the reliability would have both reliability and economic benefits in these systems. This shows a home area network. So individual home load energy management with price-based demand response. The system architecture of a home area network consists of sensors, a smart meter, and a smart plug to connect legacy appliances. So each appliance would be connected and controlled independently. We have smart devices or smart appliances, electricity storage, and electric vehicles, which we can connect and control. And we have the computing unit, the smart home controller, and the system is able to control each appliance or your EV charging time and to be able to control the demand response precisely down to minutes. This is a graph for a home area network, or HLM. It monitors, controls, and coordinates the operation and energy consumption of individual responsive appliances. And it's going to create a huge difference in your electricity bill and also the reliability. So when we speak about the smart home and future of the homes, it's going to be just smart homes. IoT plays a huge role, and all the appliances nowadays are most appliances, the refrigerator, washer, dryers are smart appliances, but they're not connected to a home area network. That's the problem with most of them. They just usually send alerts. You're able to control most of them, but since they are not controlled to the smart meter, and therefore the production side and power company, you don't have a unified home area network and control system, an integrated system, but you can control them individually. But a smart home system in the future would be able to control all these parts. And there are smart homes, the new homes, I've seen some of them sold that you can control them, especially if you have a solar panel on top of your roof and you have a off-grid system, a storage system, battery backup system. You can actually create an additional income to provide electricity back to the grid and when there's peak demand. So flexible loads, this just to summarize, different flexible loads. Deferrable loads are like washer, dryer, or dishwashers. You can turn them on in an alternative time of the day. We have the lighting loads. They can be dimmed. We have the EV loads, or essentially batteries. They could actually be used as two ways. New EVs have a two-way system. They can actually provide energy back to your home during peak hours. And then we have thermostatically controlled loads, or on-off control, your HVAC system, refrigerator, heating, cooling, etc. Heat pumps, water heaters, and so on. So different flexibilities. We have deferrable, interruptible, and variable powers, as mentioned. Then we have dispatchable demand response. Category of demand response, we have dispatchable demand response, controllable loads, like the ones that are capable of adjusting consumption per dispatch signal sent by the utility. And we have the 9 dispatchable demand response from the perspective of the grid operation. So just summarize everything. This is an example of a wholesale energy market and real-time price of ERCOT in Texas. The normal price is $10 to $40 per megawatt hour, or 1 to 4 cents per kilowatt hour. The cap limit is $9,000 per megawatt hours, or $9 per kilowatt hour. The retail electricity market, the regular electricity plan price is about $0.1 per kilowatt hours, or 10 cents per kilowatt hours. With demand side management, we may avoid price spikes or peaks. This is an example from February 2020 and August of 2019. And you can see the difference between them and in the price. So obviously in the summer, Texas is a very hot environment, so everyone turns on an HC, so you can see an significant increase in the price and the consumption, and in the winter you see a significant decrease, and you can see the price change between February and the winter and summertime. Okay, that's it for today's class. If you have any questions, just please send me an email, and I will see you next week. Thank you.